Okay. I'm very like to speak about infrared thermography and about stored dissipated energy, but in this presentation I will speak about theoretical approach. We try to simulate the problem of stored energy in the metal. And I will use the presentation of Mrs. Svideniko as an introduction for my presentation, and I just summarize what has been said in the first presentation. Now we and a lot of team can measure the dissipated energy during the tensile test. If we can measure the dissipated part, we can measure mechanical work, and finally we can measure the stored energy. In the beginning of my presentation, I will say several words about why it's interesting to measure the stored energy. After, I will present our attempt to develop an analogical model, and we'll show some example of numerical simulation. So this work is going on in the Perm Federal Research Center, and I have to say several words about research center. Now we have in Perm, we are collect several institutes, and we have pretty big center, about 1,000 people. And it's multidisciplinary center, and we have biological, geomechanical, chemical, and mechanical application. And we launch very interesting transdisciplinary research, and some of them was presented on this conference. So next slide present the outline of the presentation. In the beginning, I will say a lot about motivation, after mathematical model, and examples of simulation. So before start, just an idea about Russia and location of our institute. We are not far from Europe, just on the geographical border of Europe. It's located near our city. So if we are going to the stored energy problem, I want to repeat this excellent picture from the review of Professor Beaver. It's one of the best review devoted to the stored energy problem. All work published up to 1973 presented in this work, and it's shown that the general assumption that the plastic deformation is fully dissipated process is not very well, it's not experimentally proved. Generally, the most published work is the work of Taylor-Queeny, and there is a Taylor-Queeny coefficient in theory of plastic deformation. And this red line mark the area so-called less than 10%. Generally, the people who works in theoretics of plastic deformation say that stored energy is several percent of plastic work, and it's not interesting to take into account. Here, all experimental work with copper with completely different loading conditions, and we can see that a lot of results less than 10%. But 10% is pretty big. And if we have a look on another work mentioned in the Beaver report, we can see extremely big value of stored energy. For example, with very low temperature, it's completely undissipated. Plastic deformation is completely undissipated processes. It's published by Beaver. I have never checked it experimentally, but it's possible. And if we go to a new experimental investigation, I have to mention a team of Professor Oliferuk. She made very interesting experiments with control samples, and he measured the rate of stored energy under plastic deformation of steel. And we can see that rate of stored energy can increase up to 46% in the beginning of plastic deformation processes. Here in our work, it's dynamic loading, and we can see also a dissipated part. It's quite small for some materials. We can go further, and I would like to show this picture. It's about 40 years old. It was published in Russian books. It means the results was obtained before and about 50 years old. And this work was devoted to the thermodynamics of strength and fracture. And here, it's not very good quality, but the general idea, it's different steel under cyclic loading, and the people measured the stored energy under cyclic loading and have shown that fracture corresponds to the same value of stored energy. The stored energy, not dissipated, but stored, is a well-defined fracture criteria. Generally, if we propose the Taylor-Queeny coefficient is constant, we can say that the stored part is proportional to the dissipated part and try to measure the dissipated part as a fracture criteria. But sometimes the proportionality can change, and from this point of view, the storage is the most important part of. We have a lot of experimental attempts to measure, but here I want to start from thermodynamics. And when we try to simulate to study the energy balance in metals, we have to start from the first thermodynamic law, second thermodynamics law, and try to find some thermodynamic potential for our system. It's key question, and there are many books devoted to the thermodynamics of solid with defects. For example, there is no reference, but if you are following the way which was published by Razakis, and we propose that no effect of defect accumulation on the heat capacity, and propose that no effect of defect accumulation of elastic properties, it's easy to show that we can write the energy as a three part. One is standard, second one it's an entropy of plastic deformation. It's a very interesting parameter. And second and last one, it is thermodynamic potential corresponds to the structural changing of our system. And next question, how we can describe the change in the structure in our system. Here, during my presentation, there were several bifurcation points. For example, it's one of bifurcation point. If you propose that no effect effect of defect accumulation or heat capacity, we can write this equation. Few months ago, it was published a book by Professor Raniecki from Poland, and he has shown that if capacity is a function of plastic deformation, we can add additional items to this equation. And we spend a lot of time for measurement of function of evolution of capacity as a function of plastic deformation. So in this presentation, we forgot about heat capacity, and we will forget about entropy of plastic deformation. It's also a very crucial point, but it's quite simplified, the theoretical description, and there are some theoretical books, there are some reference, but in the middle of last century it was shown that entropy of plastic deformation is small and we cannot take it into consideration. But again, it's a bifurcation point and we have to discuss. If we continue, we can write a well-known thermal conductivity equation with two sources, thermoelastic and thermoplastic source, and we have to determine the structural sensitive variables. Quite easy to write a well-known equation of stored energy rate. And here you can see the coupling between the temperature and structure. Generally, we can, again, bifurcation point, avoid the coupling about temperature and bifurcation fraction, and practically we directly connect the stored energy and thermodynamic potential. It's not true, and there is a long discussion about is it possible to use stored energy thermodynamic potential or no, but if we are through several bifurcation points, we can use this equation, and we can, if we measure stored energy, we will have some idea how we have to write the thermodynamic potential. Another part of ideas, finally, we can propose such a thermodynamic model of the processes. It's dissipation and inequality. It was described in another presentation of people from my institute. If we use local equilibrium condition, we can write the simple equation for the plastic deformation and structural sensitive parameter. And according to our tradition, we use the structural sensitive parameter as an additional structural sensitive variables. And I'm going to show why we are use such kinematic relation for description. After we can write the Hooke's law, and we are looking for good approximation of thermodynamic potential. Why we are use structural sensitive variables as a deformation? In the beginning of 18th of 9th century, it was proposed the theory, mesoscopic theory of defects. The idea was quite old. It's Kachanov idea about ensemble of cracks. We are trying to calculate the energy of each cracks, try to do some averaging based on statistics, and we can obtain additional deformation caused by such type of defects. If we are able to solve the statistical problems, we can determine, at least qualitatively, the way of thermodynamic potential. So we have practically two different ideas. We have experiments with stored energy, and we have statistical theory of defects, and we try to simulate the stored energy evolution under plastic deformation. In the simplest case, in one-dimensional case, we can use special equations for kinetic coefficients, and finally you can see the simulation of results of Professor Polyferu, its experimental and theoretical results of stored energy evolution under plastic, under tension of steel. It's a phenomenological model, and we have very good correspondence between experiments. But we are trying to move to the next step and propose three-dimensional model, which can be adapted in the standard package, for example, in Abacus or in console, which able to simulate plastic deformation and the stored part. For this purpose, we try to combine our idea about structural sensitive variables and general phenomenological plasticity. How many time I have, sorry?
You have 4 minutes.
Okay, okay. But practically it's classical plasticity theory. They use incremental law of associated rules for our variables. We introduce plastic deformation, we introduce isotropic parameters and structural sensitive variables, and write dissipative potential for our system. Following the standard procedure, we can propose strain sensitive and strain unsensitive variables for different kinds of materials. We find the approximation of dissipation potential for plastic deformation, add some ideas about thermodynamics of defects, and here you can see, I'm not going into detail. In the mathematics, it's general. It's well-known formal approach, and we can obtain the equation for plastic deformation and for isotropic hardening, for stress unsensitive way, and in the stress sensitive way for our structural variables. Finally, we are used two different versions of our model: weak sensitive for deformation rate and sensitive for deformation rate. And this model, we have two parts. Dissipative parts, it's practically classical plasticity, and additional part which describes this energy stored in our ensemble. We can forget about Kachanov ensemble. It's just a phenomenological parameter which can be used for simulation. And here you can see where sets of equations which can be used for simulation, and some examples of our simulation for quasi-static tension. For example, here it's for different materials: arc iron, steel. It's Russian name of a steel, but it's about I think it's 304 L steel and 360 steel, so something like this. And titanium OTF4. It's also Russian mark. As I know, there is no direct connection between this Russian titanium and European. We have very good, of course, if we have a phenomenological model, we have very good results. It's the same, theoretical and experimental, but this model gives us opportunity to calculate dissipated and stored part. And here you can see the results. For example, it's mechanical parts, it's dissipative, it's stored energy rate for steel. It's very interesting. We can find some very thin parameter. For example, it's experiments, it's our simulation. Here you can see the stored energy rate. Here you can see the hardening coefficient. And there is a key point on the hardening coefficient which corresponds to the maximum of stored energy in experiments. And the same we can obtain in numerical simulation. There is a key point in hardening coefficient, and it's a maximum of stored energy rate. And next slide, I will speak just about this. It's our result. This was presented a few minutes ago. We can measure the stored, dissipated, and plastic work, and we compare the experimental and finally, we can use the same model for simulation of crack propagation based on the energy-based equation, on the energy-based approach. For example, if we consider the energy balance at crack tip, following shot of, for example, Chudnovsky, we can write very beautiful, from my point of view, equation which connect fatigue crack rate and practically the stored energy rate. And here you can see the damage energy and G integral in very unusual position under the line. And we can use this equation and we can try to simulate the stored energy for crack propagation. We did some experiments. It's just academic problem. We tried to solve the crack propagation, I guess, in titanium, no? In titanium, and we can very good comparison between crack propagation and simulation based on our equation. But it's not fully static simulation. We have a crack, make several cycles, calculate the energy for the last cycles, and estimate the energy rate. After, we take another crack and calculate it. So, summing up, all has been said. I can stress again that stored energy is a very interesting topic and very important. And I have presented a phenological model which allow us to simulate some interesting, from our point of view, problems. Thank you very much. Sorry for the time.
Thank you very much.